Good morning. This is Ms. Billerbeck, and we are going to review Singapore Math 7, Chapter 16, and then we're going to later review Chapter 17. So the first part of 16 that's super important is set notation. So sets are collections of objects like a family of cats, a pod of dolphins that I adore dolphins, and a pile of books. So set notation, we can write set A equals, and we use the wavy brackets here, cat breeds, and end wavy brackets. So set B equals wavy brackets, positive numbers, wavy brackets. So that's the way we would designate a set. So let's look at set builder notation. So this says set B equals X such that X is a positive number. Okay, so B, here's the way the book wants you to say it. B is the set of all elements X such that X is a positive number. Okay, so here's another way to write it as well that you might see in other books. So B equals all the X's such that 0 is less than X is less than infinity. So that's all positive numbers. Okay, so if X is an element of a set A, we write X is an element of set A. So we have a lot of symbols, which is shorthand. So we don't have to write all these words. So if X is not an element of set A, we write X is not an element of A. So we put a slash through this, and that means not. So whenever you see a slash through something, it means not. All right, the number of elements in set A is denoted by the number of elements in set A. So this little n means number of elements. So given the set C equals letters of scholar, this word, list the elements in set C. So we'd write C equals, and then we're going to do the wiggly brackets, S, C, H, O, L, A, R. So that's all the letters in scholar. Then find the number of set C. So the number of set C then equals 1, 2, 3, 4, 5, 6, 7. So there are 7 letters in the word scholar. So given set B equals the colors of the American flag, list the elements of set B. So set B would then equal red, white, and blue. So if we state the number of elements of set B, well, we only have 3 colors, so that equals 3. Is red an element of set B? So red is an element of B. So that's how we'd write it. Let T equals 3, 4, 5, 6. Is 1/3 an element of T? 1/3 is not an element of set T. So that's how we'd write it. Express T in set builder notation. So if we look at set builder notation, we have T equals, and then we write X, and they want to use the colon instead of the double parallel lines, which means such that. So both of these mean such that. And then these x is an integer. Between from 3 to 6. So let's write it that way, from 3 to 6. Then we've got them all. 3 to 6. Okay, so that would be set builder notation if we just wrote it out. All right, let's move on to chapter 17 now. There's more in chapter 16, so if you'd like to look at that, you're welcome to go to the videos in Singapore Math 7, chapter 16 for more information about subsets and things like that. So now we're moving on to 17 because we're doing a brief survey of early statistics so that you're ready to do your statistics project at the end of the year. So probability, there's two types of probability. We have experimental probability, refers to the probability of an event E occurring when an experiment is conducted. So that's when we do trial and error. What happens when we do this? And we write the condition, the result down. And we try it again and we write the new result down. And we collect a lot of data because just a few data points is not very helpful in statistics. So the more data points we have, the better our statistics summaries of the results will be. Okay, so experimental probability is the number of times E occurs over the number of trials. So theoretical probability or simple probability is calculated. Probability of event E happening is the number of outcomes of E over total number of possibilities. Okay, so when we do something like throw a dice, there's 6 different possibilities, 1, 2, 3, 4, 5, 6. So if we wanted the probability of rolling a 2, well, there's only 1 2. So there'd be only 1 outcome of 2 over 6 possibilities. So the probability of rolling a 2 would be 1/6. All right, so we call dice fair 6-sided number cubes. So a fair 6-sided number cube is rolled. Find the possibility of getting a 5. So our possibilities again are 1, 2, 3, 4, 5, and 6. All right, so 5 is 1 possibility. So the probability of rolling a 5 is going to be 1 possibility of, or 1 outcome of 5, and there's 6 possibilities. So the probability of rolling a 5 is 1/6. So now the probability of multiplying a multiple or throwing a multiple of 3. Well, there's this multiple of 3 and that multiple of 3. So we would have the probability of a multiple of 3 would be there's 2 possibilities out of 6, and then that reduces to 1/3 of the time we would roll a multiple of 3. All right. So it's good to write your sample space, which is what all your possibilities are. So it's good to write it down so you can visually look and see. So now we want probability of an odd number. So we have 1, 2, 3. So we have 3 out of 6, which is 1/2. So that's the probability of rolling an odd number. All right, so a card is drawn randomly from a deck of 52 playing cards. Find the probability the card is black. So if you're not familiar with a deck of cards, okay, there are hearts. There's 13 hearts and they're red. Then we have 13 spades and they're black. We have 13 diamonds and they're red. And 13, we've got clubs and they're black. Okay. And then a deck of cards goes from ace, and then it's 2 through 10, and then we have jack, queen, and king. So that's a deck of cards. Okay, so every suit has an ace, 2 through 10 cards, a jack, a queen, and a king. So let's look at the probability of black. So if we write probability black, so we see we have 13 of 13, which is 26 out of 52, which ends up 1/2. Now, probability of an ace. Well, for every suit, and we have 4 suits, hearts, clubs, diamonds, or hearts, spades, diamonds, and clubs. We have 4 suits, so we have 4 aces out of 52 cards. And that reduces to 1/13 because every suit has 13 cards. All right, so then we look at a probability of a red queen. Only 2 suits are red, and each of those suits has a queen. So we have 2 out of 52. So the probability of a red queen would be 1/26. All right, so now we're going to go look at 2 fair 6-sided number cubes are rolled. So find the probability that the sum of the 2 numbers shown is 6. So we have possibilities here of 1, 2, 3, 4, 5, and 6 being rolled, and 1, 2, 3, 4, 5, and 6 being rolled. So if we look at these and figure out, well, what would be the sum? So we have 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, and then we have 4, 5, 6, 7, 8, 5, 6, 7, 8. And then 3 plus 3 is 6, 3 plus 4, 7, 8, 9, 7, 8, 9, and then 4 plus 4 is 8. And then we have 9, 10, 9, 10, and 5 plus 5 is 10, and 5 plus 6 is 11, 11, and 12. So those are all the possibilities that we could get when we're rolling 2 dice, or 2 fair 6-sided number cubes. the sum of the two numbers is 6. Okay, so we look at all our possibilities, 6. So we have 1, 2, 3, 4, 5 6s. So the probability of a 6, and again, that was 1, 2, 3, 4, 5 of them, and there's no more. So we have 5 out of, and there's, if we have 6 here and 6 here, so 6 times 6 is 36. So 5 out of 36 throws, we would get a sum of 6. So when we look at both numbers would be the same. So this one we look at the diagonals. So 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So we count the diagonals. 1, 2, 3, 4, 5, 6. So probability same. We'd write 6 over 36, which is 1/6 of the time we would roll doubles, which is the same dice. The 5 over 5 and a 5, a 6 and a 6, a 4 and a 4. All right, recognize that. Okay, so we have a family has 3 children. What's the probability that there's only one girl? Okay, so we need to do a family tree. So we have 3 children. So with the first child, we have either a boy or we have a girl. With the second child, we have a probability of boy or a girl. Okay, these are independent, so there's nothing saying that it has to be a boy or it has to be a girl. So if you had a girl first, it doesn't have to be a boy. It's just as likely to have a second girl. So now we're going to have a third child, and we have a boy or a girl, and a boy or a girl. And this is called a tree diagram. And then we have a boy or a girl, and a boy or a girl. All right, so there is only one girl. So if we look at this, it's boy, boy, boy. So that is not one of them. But we could have boy, boy, girl, which is one girl. So that's one possibility. So let's keep that in mind. Or boy, girl, boy. Okay, so that's 2. And then this is boy, girl, girl. So it has one girl, so that doesn't work. Then girl, boy, boy, that's 3. Then girl, girl, that knocks out everything else there because there's 2 girls. So we have 3 possibilities. Okay, so now we need to figure out, well, what's the total number of times here? So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 possibilities. So the probability of one girl is 3 out of 8 possibilities. Okay, so these are all the possibilities with 3 kids of having only one girl. All boys, well, we see that there's only one. So probability of all boys, and there's only one way to do that, is 1 out of 8 times. Okay, so that's how we do a tree diagram to figure out our possibilities, all the possibilities, and then we can follow those lines of the branches of the tree to figure out how to count that. All right, so let's talk about, in a sample space, 2 events are mutually exclusive if they cannot occur at the same time. So if A and B are 2 mutually exclusive events, then the probability of A or B occurring is the probability of A or B equals the probability of A independently plus the probability of B independently. So that's like the probability of my door opening and it raining, and it rains outside. Those are mutually exclusive events. The rain does not cause my door to open. Okay, they can happen independently. All right, so let's take a look at this. How would we use this? So if we have coins that are tossed, let's find the probability of getting 3 heads and 2 tails. Okay, 3 coins are tossed. So let's do the tree diagram. So we have heads, tails, because there's only 2 possibilities. You either have heads or you have tails. Then the second row, we have heads, tails, heads, or tails, because these are independent each time. This third time, it's heads, tails, or heads, tails, or heads, tails, or heads, tails. So we're using a tree diagram to do this. So we want the probability of 3 heads. So 1, 2, 3 out of 1, 2, 3, 4, 5, 6, 7, 8. So the probability of H, which is 3 heads, is 1/8. And the probability of 2 tails. So probability of tail. So we can't have that on this branch at all, but we can right here. We have HTT. So let's write HTT. We have THT. Whoops, you can't read that one. So let's write that again. HTT. Then we have THT. And then we have TTH. So we have 3 probabilities out of 8. So the probability of HHH will go like that. That's 3. Or, oops, I forgot to write the or. Or TT. Then is 1/8 plus 3/8, which is 4/8, which ends up 1/2. All right, so that's how we figure it out. So now we have 3 heads. So we already know the probability of 3 heads or the first toss ahead. Okay, so when we have the first toss ahead, that gives us 4 different things here. The first toss ahead is head, 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 tail, head, head, tail, tail, and I think I missed one, head, head, tail. There we go. So we have head, 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 tail, head, tail, head, and head, tail, tail. So they all start with head. So there's 4 of those. So the probability of head first, haha, equals 4/8, which is 1/2. So if we add them together, probability of H, 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 or H first, then that's going to be the 1/8 from up here plus 4/8, which is 5/8. Okay. So those are mutually exclusive events when we flip a coin. Coins, dice, cards, these are all random things. It's hard to be biased when you're using coins, cards, or dice. So that's why they're used a lot, to keep everything even possibilities, especially when we do a coin toss to see what team starts. Then both teams have 50-50 chance of being successful. So two events are said to be independent events if the occurrence or non-occurrence of one event does not affect the probability of the occurrence of the other event. Like the door opening or it's raining outside are two mutually exclusive events. They're also independent events. If A and B are independent events, and the probability of both events occurring is the product of their individual probabilities. So what we were looking at before was an OR situation. So we were looking at if this happened or that happened. So in OR situations, we add our probabilities. Now what we're talking about is AND situations. If, for instance, if we rolled 3 heads and it started with H, heads first. So that would be 2 independent things. So we would multiply that. Okay, so ANDs, the probability ANDs, A and B happening, we multiply. If it's A or B happening, we add them. Okay, so a letter is selected at random from each of the words. So the words bread and butter. Find the probability that both letters selected are vowels. Okay, so when we have P, bread, vowel of bread, so we look at the number of letters of bread is 1, 2, 3, 4, 5. So we have 5 letters in bread, and 2 of them are vowels. So then we look at the probability of a vowel in butter. So we have 1, 2, 3, 4, 5, 6. And we have 1, 2 vowels, U and E. So this is going to reduce to 1/3. So now we look at the probability of both letters selected are vowels. So the probability of vowels in bread and butter, bread and butter. So we're going to multiply those. So we have 2/5 times 1/3. So that gives us 2 out of 15, 2 occurrences out of 15 opportunities. Okay, so that's what that means. When we have an and here, we multiply. All right, let's do our last example. So we have a box holds red pins and 2 black pins. What is the probability of picking a red pin and then another red pin? Now, this is not independent. It's actually dependent. So let's look at why it's not independent. So our first pick, we have 4 red pins. So red, 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 red. And we have 2 black pins. Okay, so we want to pick a red pin and then another red pin. So the first probability of picking a red pin is we have 1, 2, 3, 4 reds out of 6, which is 2/3. The probability of picking red without replacing, so that means the second red, when we look at this, or let's do second red. So now one of these reds is gone. So now we have 3 out of 5 possibilities because there's only 3 reds left and there's 5 pens. So that's why this is dependent on what the first choice was, because now we have 1 less. If we had replaced the pen, then it would have been independent. But when we do not replace the pen, it becomes dependent. So the probability of red then becomes 2/3 times 3/5. That cancels. So it is 2/5. So there you have it. So this is a dependent events when we do not replace. So you have to be careful with that. All right, that's your crash course in early statistics and probability. Have a wonderful day. Bye-bye.